Good morning, ladies and gentlemen. Thank you for being here with us for today's online event on the crucial role of supercomputing in weather and climate science, partnered with the Centre for Climate Research Singapore, Meteorological Service Singapore, National Environment Agency. My name is Alethea from the National Supercomputing Centre Singapore, or NSCC for short. For those of you who are not familiar with us, NSCC is a national research infrastructure funded by the National Research Foundation of Singapore. NSCC is Singapore's first petascale supercomputer facility that provides high-performance computing and resources to all local research institutes, institutes of higher learning, government agencies, and companies in both the public and private sector. HPC resources are beneficial in a variety of ways and in a number of different sectors. It enables research of the highest computational complexity and data intensiveness in areas like advanced modeling and simulation, artificial intelligence, and big data analytics to be completed in shorter time spans. If you are interested, do find out more about NSCC and HPC at www.nscc.sg. Research in weather and climate science plays a crucial role in improving understanding and building resilience against the impacts of extreme weather events and a changing climate. Since the earliest days of numerical weather prediction at the start of the 20th century, where human computers were proposed to predict the weather, there has been a close tie between climate and computational science. Today's talk about the crucial role of supercomputing in weather and climate science will touch on the climate challenge, the development of NWP, or numerical weather prediction, and climate modeling and projections. The increased resilience on supercomputers to deliver results and a forward look of the future where the increasing complexity, the cloud, machine learning, and the advent of novel HPC architectures will require expanded partnerships between climate, computational, and data science communities. So let me bring on screen Dr. Dale Barker. Dr. Dale Barker is the Director of the Centre for Climate Research Singapore, Meteorological Service Singapore, National Environment Agency. As a Director of CCRS, Dr. Dale Barker provides strategic direction, oversight of the Centre's weather and climate science activities, and engages with senior stakeholders in the national and international weather and climate community. Dr. Barker has extensive experience in data assimilation research, use of observations in numerical weather prediction, and regional climate reanalysis. Before we get started with the talk, please do note that if you have any questions, do post them into the Q&A chat at the bottom of your screen so that Dr. Barker can address and discuss this after the presentation. So without further ado, let me warmly welcome Dr. Barker to get us started. Dr. Barker, please.
Great. Well, thank you for that welcome, Alethea, and very excited to be here this morning. Welcome, everybody. So yes, I'd like to spend 40 minutes or so just talking about the critical role of supercomputing in weather and climate science. So I'm going to cover all time scales from the next hour to the next 100 years. And one of the things I really want to outline here is the crucial link between weather and climate. They're not separate. They're not separate activities. They are crucially linked. So without further ado, in terms of the overview, I will start off with just a statement of, I'm sure you're all aware, the actual climate challenge we all face on Earth. From a risk basis, I think looking at these in terms of risks, impacts, etc., is the way we have to be looking at this, and we can't do that alone in climate science. We have to be working with the adaptation and mitigation communities too, of course. This talk is focusing on supercomputing aspects, so I will give a brief history on supercomputing in weather and climate science. Following that, part is justification of why do we need these big supercomputers? What is it about weather forecasting or climate projections that means we need such large computers to do this? And that's related to the various forms of complexity of the climate system. I'll then move on to my new home since the start of August, CCRS, and what we're doing in CCRS in terms of supercomputing and some of our strategic activities. And then I'll close with some of the big future challenges joint challenges for the climate and the computational science supercomputing communities. Okay, so starting with the climate challenge, I have a couple of diagrams here, pictures from, you see on the top left, this is the World Economic Forum global risk report. It's done every year. And this is the latest version that came out in March, I think it was. So if you look at the slide on the left-hand side, the top risks, as estimated by around 600 groups in 80 different countries, you see this is the standard risk impact on the y-axis, likelihood on the x-axis. So the top right are the ones that are the biggest impact, the biggest likelihood. And as you can see, if you focus on the top right, of course, the climate action failure and extreme weather are highest risk. It's judged as highest impact, highest likelihood. You do note the greens, which are the environmental clustered in the top right. You see other things on there, such as weapons of mass destruction is at the top left, low likelihood but potentially large impact, and of course a whole variety of societal and other issues there. I'll come back to COVID-19 on this one because it's an interesting, you could argue, omission from this, but let me come back to that. In terms of global risk interconnections, of course, now we've said that the climate action or the lack of climate action, the failure is a major risk. And extreme weather today, of course, these risks are not independent; they are related. And so, what the diagram on the right is showing is the interaction between climate action failure in terms of global governance failure, water crises, the link with weather, of course, national governance failure, involuntary migration. Of course, this has huge implications across the whole of society worldwide. So again, it's recognized, has been so for many years now, as a major risk on the world stage. It's interesting to see how that has evolved. Those evolving risks have evolved over the past 10 years. And as the first thing you note, and this is time on the going from left to right, from 2007 to 2020. As you can see, the environmental ones in green are the ones that are clearly dominating the perception of risk by this particular activity. Now you have to go way back until 2000 and 2008 when you see pandemics. So of course this is not a perfect analysis, and of course with hindsight that would probably look a different color this year. But it does point out that this is not a perfect science. But of course the point for this talk is that it is recognized by this group and others that climate and environmental risks are huge for the world. We can look at it in different ways, and in the UK, for example, the UK has what we call a national risk register of civil emergencies. So it's a similar sort of plot. So you've got the impact on the y-axis and the likelihood across the bottom. Now, interestingly enough, here you see the top right is pandemic influenza. So depending on which groups are actually looking at this, you can pick. I presented this slide last year in New Zealand late last year, and there was almost a question of why is pandemic influenza, and there's another one in there. Where are we? Yeah, the emerging infectious diseases. That's the yellow triangle. Are they really so big? Well, of course, absolutely. I don't think we'd disagree with that this year, right? So, but putting that aside, in terms of the UK National Risk Register, you again see a wide variety of weather, climate-related aspects. So, and this is about impact over the next 5 years. So, coastal flooding, river flooding, storms and gales, etc. So, again, weather is particularly important, and climate on this aspect. So, you can measure this in different ways, but the point is, this is the framework we need to assess the risks and the impacts and the likelihoods, the probabilities. This is very much a probabilistic activity, as I'll come back to later. Of course, you may have seen some of these slides, this sort of slide. So, of course, for Singapore itself, if we hone in on Singapore, climate change is already a challenge for Singapore. You'll see the Ed Hawkins type warning stripes on the left. You can see time going from 1910 over to 2010, last 100 years. I think this is a particularly striking representation of how temperature change in Singapore has accelerated over the past 10 years or so. So on the right-hand side, again, sea levels have already risen, as I'll show on the next slide. But in terms of vulnerability going forward, the dark areas there are areas of Singapore that are below 5 meters. And as you can see, significant existential risk for Singapore itself in terms of the areas that might be inundated under certain some projections under the climate scenarios. And then that's modeling. This is real. Of course, now we look at the actual stations here, the stations there on the map of Singapore there. And as you can see, actual measured sea level rise over the past 40, 50 years or so, it is seen 10, 15 centimeters or so. And the slides on the top right showing, again, the acceleration on the global scale of sea level rise over the past 10, 20 years or so. So this is real, it's happening now. So in that sense, this is when climate change is happening now, this again is another thing that really makes the distinction between weather and climate irrelevant. Climate's changing now, it's impacting the weather today, and again, it's all part of the same picture for me. So to just take a bit of a detour into a brief history of supercomputing in this field. Of course, if you go to Wikipedia, you'll get a definition of climate and numerical weather prediction. And if I swiped in the climate models definition, the weather models, and again, you look at those and they're very, very similar. We're using the same systems essentially for just on different timescales, whether it be for the weather forecast tomorrow or a climate projection under climate change in 100 years' time. And as you can see, what the sort of techniques we use, we might break down on the globe there, we might break down the globe, the atmosphere, the ocean, and all components of the Earth system into potentially grid boxes in horizontally and vertically, and we need to represent all those different processes. So it's a very complicated system. So you're starting to see why we might need big supercomputers for this sort of application. But if we go back actually to the end of the First World War, so Lewis Fry Richardson on the left there was a brilliant mathematician, meteorologist, worked for the Met Office and also stationed up at Eskdalemuir in Scotland. He ended up in the First World War, he was actually an ambulance driver at Passchendaele, and it's rumored that he was starting to put these equations down while he was there and to look at how he might solve this. And his vision was of a forecast factory. So the picture in the middle you see there is of Richardson's, what is known as Richardson's forecast factory. So this is essentially the vision of, we didn't know about computers at the time, of course. This is the vision of a large building, such as the Albert Hall, which is on the right there. So those of you who've been to Imperial College or know the Hyde Park will have seen the Albert Hall maybe, or been there for a concert. The idea is we'd use a large building such as that and fill it with people, maybe tens of thousands of people, and they would all be doing their own little calculations of the weather conditions around different parts of the world. So you can see the map superimposed on the roof of the building, and all those people doing calculations to try and predict the weather. And the person in the middle is shining a light where there might be some particularly interesting weather, or the people in that area might be a little slow with their maths. And he's essentially orchestrating. So again, the Royal Albert Hall, he's the conductor. He's conducting all these tens of thousands of people. Of course, this never happened. And part of the reason this didn't happen, a major reason this didn't happen, of course, is because of the advent of supercomputers. So the next slide is just indicating that probably, certainly in the UK, we see as the most important forecast in history. This was the forecast for D-Day, the Normandy landings, and just to emphasize a couple of things here. One is the two maps on the bottom left is the Allied chart, and the bottom right is the German chart. And this is what I want to say here is just the importance of observations. As you can see from the Allied chart, if you can see the little dots, their observations throughout Europe. The German chart on the bottom right doesn't have any observations upstream of where the weather's coming from. And the reason for this is partly because of that little typewriter light box at the top there, the Enigma machine, which if you've seen The Imitation Game, the film with Benedict Cumberbatch, you will see how the Colossus computer was used to decipher the Enigma machine and decipher the codes for the Enigma machine. And that allowed them to decipher some of the weather records. So they actually had weather records throughout. And of course, the D-Day weather was terrible the day before. There was a break in the weather, which was predicted by the Allies, and they went for it. And it was a real surprise because the German forecast were not seeing a break in the weather. So again, this is about a lot more than the weather forecast, but it was a key part of the decision-making process in a major event of the 20th century. So in terms of the Met Office, and we could show similar slides for Japanese or the US or the European Weather Center, perhaps not going back so far, the US would be, but going back 70 years now for the Met Office in the UK. And as you can see, its peak performance flops on the left hand, on the y-axis, and time there. And as you can see, there's a fit to what we know as Moore's law. It's about an 18-month doubling of computer power, and a variety of computers along the way, different makes. A lot of these makes have come and gone. Some of them are still with us today. If you go back to 1980 or so, your mobile phone currently has more power than those supercomputers that we were using for weather prediction back then. So we've come a long way in the past 20 or 30 years. As you will see on the top right, the most recent computer at the Met Office is the Cray XC40 Plus. That's about 19 petaflop peak. It will be in service till 2022, so that's the latest. And actually, as you can see, we're actually super Moore's law over the past couple of years. And I'll emphasize again, that's partly because the importance of weather and climate on society has become recognized increasingly in the UK over the past 5-10 years, as it has in many other countries. Okay. Okay, well, what does that translate into? Well, we could look at standard forecast scores, but you know, and what this plot is essentially showing is the error of a particular weather parameter, which is the 500 millibar height, geopotential height for the southern hemisphere for December, January, February period over the past 20 years or so. And the point is that the skill of the forecast has improved. The errors have come down. So now a 3-day forecast is good as a 4-day forecast is as good as a 3-day forecast was around 10 years ago. So this is the day per decade type improvement. And again, this is pretty consistent across the centers around the world. So forecasts are getting better. But one of the aspects, of course, this is a rather busy slide, but you'll see the second peak is the weather forecast. But who cares about 500 geopotential height forecasts, right? What you really care about is the impacts and the decisions that you're going to make. So linking this up from observing the climate, observing the weather, making that weather forecast, and of course that's where the supercomputer comes in. But of course then you have to translate that, and there are a variety of peaks and hollows you have to go through that with different communities. So you can provide a weather forecast, but what's the hazard? Flooding, for example. So you need to bring in the environmental modelers. Well, what's the impact of that flooding? Well, you need to get to socioeconomic modeling then, you know, in terms of the cost of a flooding event. How do you translate? How do you tell people about a flooding event? How do you give them a warning? Well, that's where science communications comes in, of course. And then, okay, you give them the warning. What are they going to do about that warning? What decisions are they going to make as a result of that, whether it be public, environment agency, or whoever? That's where you get into behavioral psychology. So you can see this is what we call this is Brian Golding, who chairs the World Meteorological Organization's High Impact Weather Project. We call it the 5 valleys of death. You've got to span all of these bridges, invest in all of these communities in terms of getting from observing the world to actually making decisions. And what we're talking about here is really just the first 2 or 3 in terms of supercomputing. But we should recognize we're not the only game in town here. And if you start to do those sorts of analysis, you come to some quite powerful results. So this is an example of the benefits of investment in supercomputing for weather and climate. So in 2014, the UK government approved around 100 million for the new supercomputer, top right. It's installed in 3 stages, 2015, 2016. And in terms of how that was justified, the business case set out socio-economic benefits. So the end benefits of this investment in supercomputing, and it was an independent approach from Cambridge University. There's a page there in terms of the approach that was used. But in terms of the various options in terms of computer upgrade, the one that was eventually chosen had a 5-year return on investment of 22 to 1. So you spend 100 million on supercomputer, you get about 2 billion back in terms of benefits for society in the UK, not the Met Office, the UK. Now this is seen as a rather conservative estimate because there are actually only 6 case studies used in that analysis. I don't have time to talk about the details, but for example, civil aviation, they're getting a 3 to 1 return on investment, renewable energy, 5 to 1, food supply, 1-to-1, not too much there. You go across all the way to climate change and it's 10-to-1. So having information that will allow you to make decisions 10 years earlier than you would have otherwise done if you didn't have the knowledge was estimated as saving £1 billion for the UK with £100. So again, overall, it's around 20-to-1. And again, that's probably a conservative estimate. The picture on the bottom right is actually updating until a few months ago. So again, these computers only last for 5-7 years. They don't last forever. So the Met Office is now thinking about its next supercomputer and has announced earlier this year that the government has awarded just over £1 billion over 5 to 10 years for the next supercomputer, based on similar arguments as socioeconomic benefits. But again, that's $1 billion. That's 10 times the investment of the previous one. Okay, let me say a little about climate system complexity. Again, what are we going to do with that computer? You've got a big computer. How are you going to fill it? How are you going to maximize the use of that supercomputer how are you going to use that supercomputer to maximize the benefits? And of course, there are many things we could do with it. We could run our climate models at increased resolution. We could bring in more observations to improve the initial conditions or the evaluation, the research to evaluate and improve the model itself. We could increase the complexity, so as you'll see shortly, bringing in more components of the Earth system, more complicated physics, for example, atmospheric chemistry, for example, the carbon cycle. That all adds cost in terms of complexity and supercomputing, number crunching power. The axis down the bottom, we can run our forecast for longer, whether it be going from 1 week to a 2-week weather forecast or going to 200 years rather than 100 years in terms of climate projections. And the other dimension, there aren't enough dimensions on this page for this, but we have the ensemble approach, so getting an estimate of the reliability of those weather forecasts, of those climate projections. So the scenarios, different scenarios, because there is uncertainty in this system, right? As I'll show shortly. So the idea of butterfly's wings or seagull's wings, sensitive dependence on initial conditions. You can't assume that the system's going to stay linear and not end up in a chaotic scenario. So we run ensembles to assess the probabilities and the uncertainties, etc. Through perturbing the model, through perturbing the initial conditions, perturbing the observations, etc. So again, we could fill the computer up using any one of these dimensions. But what's the optimal balance? And this is where the tough work is done to optimize the benefits. In terms of the complexity, a couple of slides here from the previous IPCC report. As you know, the physical drivers of climate change, there's a lot going on. We have clouds, we have variations in solar output, we have the increases of greenhouse gases, of course. We have surface emissions, we have changing surface, we have changing albedos, all sorts of stuff going on. And of course, as we go forward with our scientific research, we increase the sophistication and the modeling of those processes, add new processes, increase the sophistication, the application, etc. And on the right, you can see just a timeline from the mid-1970s of how the climate models have evolved in the various assessments over the past 30, 40 years or so. So back in the 70s, essentially the atmosphere and the land and the ocean. And then, of course, as you get more compute power, you understand more of the science. You realize that things like aerosols, volcanic eruptions, for example, have an impact on the climate, and so you need to represent them. Excuse me. Getting into the carbon cycle, of course, dynamic vegetation, how will changes in ground cover, etc., influence things. These will change and influence the climate. So as you can see, over the past 10, 20, 30, 40 years, the complexity of the Earth system model is actually increasing. And that's right as we learn more science and realize there are more interactions that we need to cover to improve the accuracy of these projections. So that's the complexity axis. We also talked about the uncertainty, the probability of something happening. And there are various sources of uncertainty. What scientists mean by uncertainty is different to what the general public see as uncertainty. When you talk about, and again, this is where scientific communications comes in, I think, uncertainty to the general public means you don't really know. Whereas to the science community, it means, well, we accept this is a risk-based assessment. We have to look at likelihoods of things happening. And so essentially, this is a slide again from IPCC, looking at the various sources of uncertainty in climate projections of global mean temperature on the left. And of course, the biggest uncertainty in green is we don't know how the scenarios, how are we going to react to the challenge of climate change? So this is not about necessarily climate science. This is not about natural variability. The orange is the natural variability. It'll be El Nino or changing weather patterns or such stuff. This is natural stuff that's happened forever. You know, that's the orange. That's a relatively small amount of uncertainty. Now, the models themselves, yes, they're not perfect. They have uncertainty too. And that's why we use multiple models and with different modeling systems from different countries, with different parameterizations, etc. And as you can see, the model uncertainty is fairly large. It's around 1 degree in that scenario, 90% uncertainty range. But the biggest uncertainty is what we do about it. It is about, you know, are we going for limiting to 1.5, 2? Will it be 4-degree temperature rise, etc.? And how are we going to respond? And this is often the case in complex system where humans are involved. That, you know, the biggest uncertainties are things that, on the one hand, we in principle have control over, but on the other hand, are often the most difficult things to do the science on and also to actually make progress in. But again, you can see and this is why we have the various sources of uncertainty. Resolution is one. I'll just give an example from high resolution weather prediction now. So on the left there, you have the top left is a picture by J. Turner. It's the Lake District. It's a 19th century painting of the Lake District, and the topography maps underneath are the Lake District at different grid spacings. So the 12-kilometer, essentially the beautiful Lake District looks like one big hill about 300 meters high. I don't think you'd get so many visitors there if it looked like that. But of course, this is all you can do when you only have a 12-kilometer model. If you look at the slide on the bottom left, which is approximately where our current weather prediction models are, so they can run at much higher resolution than the climate models because they're local and they're only running for a few days. They're not running for decades, right? So you can see much more of the actual detail. Now, it's still not the full detail. Scaffold Pike is over 800 meters, but you can start to see you get a lot more detail. And in the UK, where it rains essentially correlates with where the hills are climatologically. So you can see in the middle panel there, if you got the 12-kilometer, the rainfall is pretty underwhelming. But if you can start to resolve some of the topographic effects, you do start to see the interaction of the atmosphere with the land surface, the orography, and so you do start to see some significant intensities of rainfall. So on the right is a forecast. You can see that animation. Hope it's moving for you. And again, you can see this is the actual forecast for that day, Storm Desmond a few years ago. You can see the red area in the north of England there. That's the Lake District. So you can see the actual forecast was actually predicting the system's moving through, but you can see that the hills are fixed clearly. And you can actually see that it is predicting several days in advance some really heavy rain out. We just couldn't see that without kilometer scale weather forecasts. Now, our climate models are not there yet at these kinds of resolutions, but as we moved into regional climate modeling, and I'll have an example from Singapore later, we can start to really represent the local weather conditions that are prevalent in a particular area. This may take a while to upload again, but on the left-hand side, again, it's an ensemble. So we're actually running, the Met Office was running 12 forecasts at the same time with slightly different initial conditions and model physics. And that gives you that uncertainty information. And people can use this information, the forecaster can use this information. They can see what we call postage stamps. They can see this system's coming through in all the ensemble members. So however we tweak the model, it's still coming up with heavy rain in northern England. And so that's useful information beyond a single forecast. What we're not trying to do is predict exactly where and when the rain is going to fall, because this is a highly nonlinear system. But what we need to do is, on the right-hand side, provide probabilities. And that's a probability, accumulating that ensemble information, of 24-hour rain above 100 meters. And you can see it focuses down on the Lake District in southern Scotland. So again, these are kind of products that, in a probabilistic space, in terms of risk, likelihood, and decision making, these are the sorts of ways you want to spend the supercomputer power to maximize benefits. So I'll just talk for a short time on CCRS. Introduce CCRS. So Centre for Climate Research Singapore was founded in 2013 under the Met Service Singapore. We're over in Kim Chuan Road at Tai Seng Metro. The mission is to advance scientific understanding of tropical climate, variability and change, and its associated weather systems affecting Singapore and the wider Southeast Asia region. So a few key words there. It's about research. It's about scientific understanding. It's focused on the tropics. It's focused on Southeast Asia, tropical climate variability, the natural variability as well as change, of course, going forward. And again, it's associated weather systems. This is not just about what's going to happen in 30 years' time. It's about what's happening the next few hours. And that last part of the mission is really key too. So we're not just doing research. We need to use that knowledge and expertise to benefit decision makers in the community. So again, it's all about that the valleys of death and working with the community to ensure that these weather forecasts or climate projections are actually used and benefit downstream users. And our vision to be a world-leading climate centre in tropical climate and weather research. So over the past month or two, I've been working on a new representation of the CCRS strategy, which I see as 3 pillars, and you could apply this to many institutes, I think, working in this space. It's an organization that does research, and to do that research, at the bottom, you need capabilities. And what we're talking about here, one of the capabilities we need here is the supercomputer, and that's what we're going to focus on here. But of course, we do that research with the capabilities, and then, of course, we're here to do science for service. And that could be aviation, government agencies, the public, businesses, etc. So again, similar to the UK, you saw the end users earlier, potential end users, the benefits. And again, we're a rising number in this region too, of course. In terms of the science to services, just a couple of examples here. Air quality prediction. At the bottom left, I've shown the animation from the UK. There's an animation of a Sumatra squall from the local system, which is known as SINGV. Again, it's it's actually a 22-member ensemble, but you're seeing 12 of the members there. So again, you're seeing. It's not. The point is, one forecast would give you some information, but when you're running an ensemble, you have information on the probabilities or the likelihood, and that gives you a much more useful information in terms of likelihoods and impacts. Of course, this is over a relatively large region, so in terms of future research, etc., focusing on urban scales, so the Isle of Singapore itself is one of the key areas of research going forward. But that was a system that was I've been working with Singapore and the Met Service for the past 6-7 years on that, so I'm very pleased that it's now operational, and we can take that forward for operational weather users. On the right, we have, again, the climate timescale, so climate change policy advice and the impacts modelling, which, again, those valleys of death, we absolutely need to span at climate scales as well as weather scales. So I won't dwell too much on this one. The 4 pillars of underpinning capabilities for me are the observations. You can't do anything without observations, really, right, in any form of science. The models themselves, and of course in this application it's weather climate modeling system, and again you see the complexity of the modeling system in the lower left. The supercomputing, which I'll talk a little about now, and the other part, and what I see as the most important one, are the people themselves. You've got observations, models, computers, and none of that works without the people. So that's in-house, and also, of course, partnerships, national partnerships with IHLs or regional partnerships with ASEAN, the ASEAN Specialized Meteorological Center, for example, is in there. WMO, global organization, and of course, particular universities and institutes externally. Of course, NSCC is a partner for our supercomputing capabilities. In terms of the strategy for modeling, I've said it a few times now, but the weather and the climate is a continuous spectrum for me. It's all about timescales. The fundamental science is the same. It's Newton's laws of motion. It's Navier-Stokes equations. The involvement of particular processes at different timescales may change. So we don't worry about climate change when we're providing a weather forecast for tomorrow, for example. But of course, fundamentally, there's a common system. There's a huge leveraging that can happen if you're developing a modeling system that can work for the next hour all the way through to the several decades ahead. You can see the various things we're trying to do. The focus will be slightly different at different forecast ranges. But the point is that if you've got a seamless weather climate prediction system, you can leverage scientific developments and understanding across the timescales to provide a consistent message with consistent science. And as part of that, in terms of the Earth System Model, the Met Service Singapore is an associate member of the Unified Model Partnership, and the picture there just shows the current list of partners across the world with the Unified Model Partnership. So again, this is using the Unified Model, which is a seamless weather climate prediction system. So obviously Singapore, can't quite see on there, but Singapore's focus is, of course, regional high resolution. I lived in the UK, so I think that was a relatively small country compared to some of our partners, such as Australia, and our focus, again, at the Met Office was both, actually. We ran global simulations as well as local. India is a major partner, so we leverage work that's done in India for the Indian monsoon, for example. We've just finished a 40-year regional reanalysis with India. The Australian Bureau of Meteorology has also completed a 40-year regional reanalysis over the area. So you can look at use past observations to understand climate variability over the past 40 years or so. So again, the leveraging of this partnership means we have around 30, 40 people, it's going to be 40 by the end of next year. We can leverage over 1,000 weather and climate scientists working in the same modeling system here. So I think that's, again, the role of partnerships in country or regionally or nationally or internationally is absolutely key. So in terms of our current supercomputing, we have an in-house HPC called Athena, and that's mainly used, or increasingly used, for operational runs. We can't necessarily outsource the operational stuff, but certainly in terms of R&D, we can look at other machines. But the Athena machine is running the operational weather forecast system. In terms of our next supercomputer, the in-house one, I'll come back to the electricity bill, but at the moment the power bill is becoming too large at the floor loading in the building. We can't house the next one, so we'll be looking at a new computer over the next year or two to increase the compute power and storage for our in-house weather systems. Now, of course, we're very excited to partner with NSCC for the Köppen allocation for climate, essentially mainly for climate studies. For example, the V3 climate projections, I'll come back to those later. And again, a really exciting development there with some initial capability right now, but sometime early next year, really going to ramp that up with some significant increases in compute power on the NSCC machines. So very excited on that. Yeah, just a little more on the third national climate change. I mentioned V3. So again, looking at regional climate, how will climate change in the region? How can we model that? What's the likelihood? How can we influence decision makers? This is really a national assessment of the effect of climate change on Singapore and the surrounding region. You can see the domain to the bottom right there. And this will be completed by the end of 2022 in time for the next IPCC assessments and also national requirements. So of course we are regional here, so we need to what we call nest this regional modeling system inside the global CMIP models from the WCRP. The global climate models are run by others. And of course, what data we produce, what times, etc. Again, it comes back to that: how are we going to use this data? Just running a forecast and then or a projection and providing the data is insufficient. as I'll come back to later. We need to look at priorities, we look at needs and feedback and optimize the output so it best suits needs. And one thing I'll highlight in terms of the seamless system, the last bullet, over the development of the weather prediction system, the SING-V system over the past 5 years, we've actually really advanced some of the science with the unified model, and Singapore has led that that tropical science development together with Australia and the UK. And what we're seeing now, which is great for climate, these climate projections, we can use that new science for the longer range projection as well. So it's a seamless system, so we can leverage the weather for the climate and vice versa. So in terms of future challenges, I'll finish with some future challenges. I've alluded to the big data issue. And of course, weather climate data is big data. And this is an example from the weather timescales, but the global model at the Met Office produces 690 gigabytes a day. The local model's around, well, quite a bit more than that, 3.2 terabytes. There's a total daily output of 4 terabytes. And we have perhaps 20 forecasters on the bench. What are they going to do with 4 terabytes of data? Of course, the answer is, well, it's the guy on the right. You know, he's got that big tidal wave coming in, and he's got a wave of data. What's he going to do with it? Of course, we have to prepare that data, process it, condense it, use data analytics, use data sciences to provide the sorts of outputs that he or she need to make their decisions. So a role for data science and AI in that process. Now, one of the strategies here is, one of the things we have to do is decouple the data. So at the bottom in the colors, we've got the red raw data, and again, that's the 4 terabytes. What we can do actually is standardize that data to not just reduce the data volumes, but just condense to what the gridded fields that downstream users are interested in. And we might also agree internationally that we should all produce our data in the same standard model format. This is what we're trying to do through WMO, for example. I think that's an honorable effort going on there. European open data policy, for example, standardizing data sets. And then we can use multiple models together without having to worry about the technical differences. There's a role here for the cloud and bringing the application to the data and not vice versa. So for example, at the Met Office, the supercomputer produces the raw model data, but it stays on the supercomputer. The data is converted to standard data and it's shipped off to Amazon Web Services, where one can access the data through APIs, etc., and through tools that are available to the community. So again, there's a role of where do you put the data, how do you post-process it, and how do you blend the different forecasts. But all this falls into place somewhat if you standardize the data to remove the differences of the initial models themselves. Yeah, of course, supercomputers are increasing all the time. That big computer, the Met Office, was number 11, I think, when it first went into the top 500. It's now down to number 33 or so, of course. If you look at the big machines these days, this is the latest June 2020 top 500. The Fugaku machine in Japan is number 1. And on the right there, I had some input from a colleague at the Riken Institute in Japan, Takemasa Miyoshi, and he's using that machine actually in research mode to run thousands of members, 1,000 ensemble members on the globe at around 3.5 kilometer resolution. Now, having the model do that is one thing, but actually having the architectures that can actually effectively data mine that information is another thing. So in terms of the architecture for Fugaku compared to the K machine, it's not only 100 times as big, but it also has the architecture which is more suitable for machine learning approaches. Okay, some of these new machines are quite different architectures, and so our modeling systems, so for example, this one here, the unified model, has been around for around 30 years now. They're getting a little old in the tooth. So it's going to be a tremendous effort to bring those modeling systems with the science that's included within them into the new era of new supercomputers. So Met Service Singapore, a part of the ZD5 Model Partnership, will be engaging in a major activity over the next 5 years to move the weather and climate science into this new system known as the Next Generation Modeling System, which on the weather timescales at least, we hope to retire the by 2025. Climate might take a bit longer, but again, this is driven by the technology. It's not driven by so much by the science. It's about scalability, it's about portability, etc. Okay, this is my final slide, and probably the one that, if anything, I wouldn't say it keeps you awake at night, but that there is the issue about, we are a climate science community that we absolutely endorse sustainability, and we need to practice what we preach. You'll see on the right that, of course, the top 500 now is a green top 500 list, because some of these supercomputers are producing huge amounts of CO2, right? So the Met Office example there in the second bullet, it's about 8 megawatts now. It's around 20,000 tons of CO2 a year. So what are we going to do? How are we going to solve this paradox of wanting to improve the climate science, to provide the information that decision makers can make their decisions, without being part of the problem as well? And there are two aspects of it, I think, and probably more. The new technologies, of course, a lot of this is driven by greater power efficiency. So some institutes now using flops per watt as part of the tendering process. And as you can see in the green top 500, it's ordered by gigaflops per watt. So those sorts of metrics are going to become increasingly important in procurement of supercomputers going forward, as they already are. So that's the new technology, that's the hardware and the technology. Upstream from that, of course, how are we going to power these machines? Ideally, if we can power these machines from renewable energy sources, then of course that partly solves the issue. That's a great solution for some countries. Iceland, for example. So the picture on the bottom right is actually the Danish Met Institute's supercomputer, research computer, which is housed in Iceland. And that's for two reasons. One is it's cool, so it's easier to cool. And the other reason is it's hydroelectric power, so it's renewable. So again, that's a great solution for some countries, but not for others. And of course, for operational systems, you don't necessarily want to ship your operational system internationally. But the final point I'll make there is the role of the cloud again here. And there is perhaps a naive vision that, it's not naive for research, but we're already doing it. So you have a globally distributed HPC network where you don't actually know which machine it's running on. You don't actually know which country it's running in. You just ask for a certain number of node hours on your application, and it happens, and you pay for it. And then you either process the data in that cloud, or you pay to have it taken off, which is expensive. But again, the principle is, you can envisage a system there. Now, when I first heard about this, I was thinking, well, that's never going to work for people like defense and operational systems. And I got a scary answer back from the person at the Ministry of Defense in the UK. He said, well, it'll take one bomb to take out your supercomputer. But if we can access a system that is distributed around 20 or 50 countries, or 3 or 5 countries, then that's a lot more resilient than what we have now. And the security issues are, in some sense, not so large. So a bit of a sobering thought, but it is true that I think generally the point here is that I think there's a role for the cloud and some of this stuff. But again, how green can we be with supercomputer, I think is going to be a major challenge going forward as these machines get bigger and bigger, and our requirements from climate science get more and more. So with that, I will finish there, and thanks for listening. I will take any questions.
Okay. Thank you, Dr. Barker, for the great and insightful sharing. So I think we've got 4 questions. Let me start it off. So the first question is, what's your view on GPU computing for weather and climate field?
There is definitely a place for GPU architectures and other type of architectures too. Some of these, it partly depends on what the problem you're trying to solve is. So some of these data mining, some of these post-processing applications naturally work best on GPUs, just the way they're lots of processors, not much on core memory, etc. So it partly depends on what you're the problem you're trying to solve, but absolutely there is a place for GPUs. I guess the other point I'd make, and I'm not the supercomputer processor chip expert, but I think some of these new technologies are coming out with combinations of both. even on the same board or chip. So I think, it won't be one or the other. I think it's going to be a combination of application and a combination of hardware solution. But absolutely a place for them, absolutely.
Okay. The next question. Do you foresee the AI adoption on the daily weather forecast routines? If yes, what will be the suitable supercomputer for this? Could you share your ideas?
So if we talk about AI, we tend to focus on machine learning, and this is data science. And the first thing I normally say with this is we've been doing, the weather and climate people have been doing data sciences for decades, right? I mean, we use statistics, we use probabilities, we use MOS systems, we use Kalman filters. Data assimilation is a data science, the optimal combination based on Bayes theory, which is the fundamental underpinning of a lot of the machine learning, supervised machine learning stuff. So I think the first point is we've been doing it for quite a while already. I think they talk about waves of AI. It was very popular in the 90s and went away. It's coming back again now. Absolutely, we can make more use of machine learning. And again, I will say we are doing so in many different ways. Now, some suggest that we don't need these expensive weather models or climate models anymore. We'll just use an AI system to predict climate change. I wouldn't go that far yet, but again, at the end of the day, the laws of physics are very powerful. Ignore them at your peril. But there's a happy middle ground, which I think is where many of the centers are at in climate and weather centers. So, for example, the radiation scheme, long-range radiation scheme inside the unified model is Socrates radiation scheme. It's quite expensive. It was coded by somebody about 20 years ago. We don't quite understand. It's not fully documented, and it's not based on the fundamental laws of physics. So, as an activity to actually consider replacing that subroutine, quite a large algorithm, but with a machine learning algorithm. Now we did that. It was quicker, it was simpler, and it was less expensive. So under the hood, there are many applications of machine learning. Post-processing is another one. I could talk about post-processing, blending bias corrections, etc. Observation pre-processing is not particularly exciting science to sit there and watch a million observations come in every day and try and pick out the bad ones. This is again an interesting area for machine learning approaches. So I think it's a very exciting time, and we should build on what we have. We have lots of data. We can train these algorithms, and we can use the basic fundamental principles such as Bayes' theorem to make these to explore these applications in weather and climate science.
Okay. Next question.
Hope to answer the question.
Has a similar cost-benefit analysis for weather or climate services been performed for the Singapore or Southeast Asia context? Would you expect a similar O10x benefit?
I've been here 2 months. We're going through that process now, actually, with looking at future computers. If you look at the sectors that are currently making use of weather prediction, of course, the science is different. The priorities are different. Rainfall is key to the UK too. The challenges, perhaps the weather on the weather prediction timescales, perhaps the science is less mature than it is in mid-latitudes, and possibly harder, more use of ensembles required. So you really have to rely for this localized convection. Yeah, we have a lot here. You really have to look at these ensemble approaches. But in principle, I absolutely I don't see why not. I see this as I think it'd be a great thing to do with the broader community. The Met Office cost benefit, I should say, was not done by the Met Office. It was done by an independent company who came in, consultants came in and used that approach to assess the benefits. That approach could be applied. I'm not aware of anywhere in the world I'm sure it has happened, but I don't have examples from elsewhere in the world. But in principle, absolutely, look at all the sectors who could benefit from weather and climate information.
We have a few more questions. You mentioned Fugaku in the slide. Could you share your views on software part, for example, UMWRF running on Fugaku? Do you see any computing benefits on this architecture? So
I think, again, one of the, as Takemasa has said, I think just in terms of the architecture, it has a combination of chips. we can really explore machine learning on those types of machines. So you know, you can produce huge amounts of data, which perhaps uses traditional chips, just lots of them, CPU type chips, to produce the independent. You know, you can run 1,000 forecasts independently, and then how are you going to combine all those data? So I think so for ensembles and machine learning, for example, how do you combine that data? I think that's an amazing resource. So it would be wonderful to have a system that you know, could take, again, it's what you do with the big data, right? It's not so much about how you produce the big data, because as we go more and more ensembles, essentially you just buy more and more kit and you have 1,000 or 10,000, then it just becomes an electricity bill issue. You don't have to use the entire machine for one forecast, right? But the challenge is increasingly be how you're going to combine the information from the different big data sets, the different ensemble members. So I think that's where these new technologies with the data science are really going to help. And Fugaku is a classic in that regard.
Okay, we have, I think, 3 more questions to run through quickly. So with the ongoing changes in temperature and sea level, what key risks do you foresee that Singapore needs to prepare in terms of vulnerability?
Well, of course, sea level rise, you've mentioned it there, preparing for sea level rise, not just the average, but you know, those extreme events. You've got to add waves and surge too on top of that. So you've got to look at the extreme events, not just the mean. So, and you could say that about multiple changing rainfall, but sea level rise is clearly one. Rainfall, again, looking at the impacts on sectors, you look at the water, you look at impacts on biodiversity, as well as sea level rise. You look at impacts on health, temperature, stress, etc. So these are, you know, these are issues that are issues for all humans in society, right? But again, certainly in Singapore, and we'll be talking more about that in future presentations on how we might use these climate simulations, for example, and the science to address or work with the community in the in Singapore, the IHLs, etc. How we work with those, bridge those valleys of death into those different communities, and work on the impacts. But yes, sea level rise, biodiversity, health, energy, etc.
Okay, one final question. What's the key performance bottleneck in terms of HPC algorithms and parallelization?
So it partly depends on the computer. It partly depends on the timescale. So for weather, if I'm trying to produce a weather forecast for tomorrow, again, it depends on the modeling system, but I'll talk about what I'm familiar with. This is you've got to get all the observations in from around the world in around 20 minutes. So that's a challenge in itself, right? That's a bottleneck, getting the observations in. You then have to process it and produce what we call an analysis of the current state of the atmosphere. And we have to do that within the Met Office, and it's similar to CCRS. You have to do that in a space of 10, 15 minutes. Because if you're late, your forecast is useless, right? So you need to have that fast. So, and then your computer, your forecast will run on the computer. I think in terms of regional models, I think that scales fairly well. I think the real problem is actually that understanding what's happening now. And we use techniques such as variational data assimilation, which are not particularly scalable. And it's one of the drivers for making more use of the ensembles, because they are, don't like the phrase, but people call it embarrassingly parallel, right? You just run 100 or 1,000 in parallel. They don't need to talk to each other. But ensemble data assimilation can do that, but the current variational systems we have are not scalable. So I would say in the current system, the big concern is over the data assimilation, those initial conditions. And of course, at climate timescales, you don't do data assimilation particularly, so you'll get a different response. It's much more about the model. So some aspect of the physics, for example, depending on the modeling system again, and the computer and the application. But you know, as part of the reason I mentioned earlier to work on the radiation scheme, to put a machine learning algorithm in there, because it was actually not scaling very well, and again complicated, so reducing the cost, etc. Yeah, I think the other aspect I haven't talked about is looking at precision. So one way to reduce this is a lot of the systems are default double precision, sort of 64-bit numbers. You can actually not all of the systems need 64 bits. So actually having reduced precision in parts of your code is a great way And physics, again, is a classic here. It's a great way of increasing the scalability of your system and the efficiency of your system.
Okay. Sorry, Dr. Barker. One final question from Anupan from the Solar Energy Research Institute of Singapore. Thanks, Anupan, for the questions. I'm interested in zero forecasted data tailored to Singapore climatic conditions. Is it possible for us to have access to climate projections data for research purposes?
Again, I'm just coming up to speed with data policies, etc. But I think if you look at my final slide in terms of that decoupling the model and the downstream data, I think generally it's got to be informed by data policy, right? But the data strategy, whatever the policy, would have to be to decouple, because it is just not practical to provide the data. You can't provide everybody access to the HPC, and you wouldn't want to, because you change your modeling system and then it breaks for people who are using that hardwired data set. So I think you need a data strategy which is decoupled. Generally, I'd say that to any group producing large amount of data, and then your data policy will decide how, once you've solved the technical issues, how one can access that at which stage, on what platform, etc. But I'm not yet enough aware of what the particular data policy would be in this area, so I can't directly answer the question, I'm afraid. It depends on research and operational data too, of course.
Okay. Thank you so much, Dr. Barker, for such a great sharing and for answering all the questions. And thank you to everyone for the ongoing questions. Before we end off the webinar, I would like to bring in our Chief Executive of NSCC, Tan Tin Wee, to say a few words.
Hello, everyone. Thank you very much, Professor Barker, for that scintillating exposition at a very broad scale of what climate and weather research and that interface with HPC. A number of people in the audience are actually key leaders in this field in Singapore. For example, Professor Adrian Law, I noticed that he's online, and Professor Adrian Law is director at NTU, a director of the Environmental Process Center, and maybe he would like to comment also about how these aspects of common interest can interface with CCRS and the Meteorological Service of Singapore to create that vibrant environment for weather and climate research here in Singapore.
Yeah, thanks for linking me up. I'm very fascinated by, actually, I'm involved in the ASEAN Hydroinformatics Center. And there's a lot of discussion on how to better coordinate hydroinformatic communication so that we can help the region to better prepare for climate change. So I believe that I'll be talking to Professor Barker very soon about how we can maybe get access to some of this information, and in fact, perhaps how to link up with CCRS in the activities for the ASEAN Hydroinformatics Center.
That's good.
Thank you very much, Professor Law. Professor Barker, thank you again for addressing this very interested audience with a lot of probing questions in terms of HPC. May I just reiterate that we are fully behind you in supporting your underpinning capabilities insofar as supercomputing is concerned. And thank you recently for supporting this renewal of contract, expansion of the contract with between NSCC and NEA.
Pleasure.
Your team is also represented in our procurement process. And as many of us in the audience know, NSCC has just launched recently another call for research projects. And I'm happy to note that there was one proposal for AI projects coming from NEA. I think it was Jeff Lowe who applied or something. So we're happy to expand on this and call upon the community out at large to actually seriously consider putting in applications for allocations of CPU hours, GPU hours, AI systems, and so on, and including your storage of your precious data on our systems. And we already have received funding, and we are wanting to turn that funding into better use for all of you in the community. I also noticed that Saris is also in the audience asking a number of questions, and I really appreciate that the solar people are actually, solar research people are actually actively also considering. I also note that there may be some folks from IHPC who are also involved in climate modeling of what we call virtual Singapore. And I was wondering, Professor Barker, whether how big a role CCRS will be playing in this process. As you know, there is a new renewal of a new institute in the you may have of Professor Gerhard Schmidt, right? And he's part of that Cooling Singapore project, our collaboration at the NUS campus, Create campus with ETH Zurich.
Yeah, so I don't know if Aurel Moisey is on the line, but he can say a bit more. But we certainly have links to the Cooling Project in Singapore. And of course, going forward, the strategy is to move to higher resolutions urban meteorology. I mean, that's going to be a big frontier going forward. So whether it be urban heat islands, sea breeze effects, or whatever it might be, in terms of the consistent with the strategy of CCRS, as I mentioned earlier, in terms of the world-class research focused on Singapore for the benefit of downstream users. I think, there's a state. I think what I want to do over the next 3-6 months, as I get my feet under the table, is to learn more and talk to stakeholders, potential stakeholders and users about, and understand more about particular projects. Because I think it's a very exciting time, and Singapore is certainly one of the reasons I'm here is because the attitude of the Singapore community to these sorts of issues is inspiring. So, I think we've got a lot to do together, and I'll be very much looking forward over the next 3-6 months as we hone the strategy and the priorities to work with various groups in IHLs or sectors, etc. Absolutely. But in terms of the Cooling Singapore, if somebody on the line might want to say a bit more about the CCRS links.
Right. Thank you so much, Professor Barker. Thank you for the audience, for really enthusing the audience in this regard. Thank you.
Thanks.
Okay, everybody, thank you so much for all your time, and thank you once again, Dr. Barker, for such a great session. Do also join us for our next webinar, Harnessing the Power of Supercomputers to Advance Marine, Offshore and Renewables by Dr. Sing Siu Ting from A-STAR's IHPC. That's all for now. See you at our next online event. Bye.
Bye-bye.
Thank you. Bye.